We talked about a couple of different kinds of equations or reactions, combustion reactions, and reactions of halogens and alkali metals. And we're going to talk about acid-base reactions and gas evolution reactions. So in an acid-base reaction, we have an acid and a base that are reacting with each other. And an acid and a base will neutralize each other, so this is also called a neutralization reaction. So we have the acid reacting with the base, they neutralize each other, and they're going to produce water and an ionic compound, generally a soluble ionic compound. A gas evolution reaction, as the name suggests, a gas is going to be evolved or a gas will be produced when this reaction occurs. And we often observe this as bubbling or fizzing. So we observed a gas evolution reaction when we dissolved our copper wires in nitric acid, right? It formed not hydrogen gas, it was NO2 gas that bubbled out, and then we saw that brown smoke go up into the hood, right? A lot of gas evolution reactions are also acid-base reactions. So some chemical reactions fit into multiple categories. Well, we need to talk about a little more about what is an acid. There are different definitions of acids. The Arrhenius definition is that an acid is a substance that produces hydrogen ions in aqueous solution. So all of the acids that we learned that start with H in our nomenclature lessons, these are all Arrhenius acids. They form hydrogen ions when you put them in water. So an example here would be hydrochloric acid. So this will ionize, it's a molecular compound, but it ionizes and forms hydrogen ions and chloride ions. Well, this is sort of an oversimplification, because let's think about what is a hydrogen atom? How many protons does it have? One. And how many electrons does it have? One. So if the hydrogen atom becomes an H plus ion, that means it lost its only electron. So what's left? Just a proton. That's a little teeny tiny thing. That is way, way smaller than a hydrogen atom. I think of these hydrogen ions as being like newborn babies, right? They don't go out in the world by themselves, right? You ever just see a newborn baby strolling down the street? They can't walk, right? They can't do anything for themselves. They're always with somebody else. So hydrogen is like that. He's too tiny to be out front by himself. So what happens is that hydrogen ion is actually going to get a ride on a water molecule. The water molecule is going to be holding the hydrogen ion and carting it around because it's too small to be out by itself. So when that happens, we get an H3O plus ion, and this is called a hydronium ion, H3O plus. And here we have an illustration of that. So this is a water molecule, and this is a water molecule holding an extra hydrogen ion. So that's the hydronium ion. So we understand that we can write a chemical equation like this, but that hydrogen ions in aqueous solution are actually not just by themselves. We understand that they're riding around on the back of a water molecule. So many chemists are going to use H plus and H3O plus interchangeably. And I know that can be a little confusing to students, and I'm sorry about that, but we like to use the H plus because it makes writing the chemical equations much simpler, and most students are on board with that. Okay, so there's that. Polyprotic acids. So poly means many, and protic refers to protons. Well, that hydrogen ion is a proton. So a polyprotic acid has more than one hydrogen ion. So sulfuric acid, H2SO4, is a diprotic acid. It has two protons. So when this ionizes, it can form two hydrogen ions, not just one. H2SO4 is one of these strong acids. It's strong in the first hydrogen ion, not the second and You'll need to know that in Chem 1B, but not yet. Yes?
Said something about sequentially, so first, so it gets rid of the, so it gets, or proton
Yeah, it
first,
loses one proton first,
and
and then it loses another proton.
okay.
Yeah.
So it goes to HSO4, and then it goes
Yeah. And like there are triprotic acids like phosphoric acid, and it will lose one hydrogen to become dihydrogen phosphate. And then that can lose another hydrogen to become hydrogen phosphate, and that can lose a hydrogen and become just phosphate ion.
What is that, 1B too?
That's really mostly 1B.
Good God.
Yeah. and that's not even the half of it. I love it, but I'm not normal by any stretch of the imagination. So that was the Arrhenius definition of an acid. The Arrhenius definition of a base is something that produces hydroxide ions in aqueous solution. So sodium hydroxide. So this is a soluble ionic compound, and the two ions here are sodium ion and hydroxide ions. So we put this into water, and this separates, and we get hydroxide ions. That's why this is a base. There are other bases, such as NH3, that do not contain hydroxide ions, but can form hydroxide ions by pulling hydrogens off of water molecules. So just be aware that those are out there. Some bases will produce 2 moles of hydroxide for every mole of base. So we would call that a diprotic acid. There's no word for a base. We don't have any special word for a base that has 2 hydroxides. But you can tell what they are by looking at the chemical formula. So this is a metal hydroxide, and it's soluble. And so when this dissolves, it's going to form 1 strontium ion and 2 hydroxide ions. So when we have an acid-base reaction, the acid is producing hydrogen ions, and the base is producing hydroxide ions. And what happens is the hydrogen ion from the acid is going to combine with the hydroxide ion from the base to make a water molecule. So here we have hydrochloric acid and sodium hydroxide. So if we look at the ions that are present, I'll do this underneath, I guess. We have hydrogen ion and chloride ion and sodium ion and hydroxide ion. And we can actually predict the products in the same way that we predicted precipitation reactions. Let's just try swapping the partners, right? So sodium and chloride together, hydrogen and hydroxide ion together. So sodium and chloride ions would make sodium chloride. Hydrogen ions and hydroxide ions, not as obvious. Well, what happens when you put those two together? Well, you get HOH. Huh. Wait, that doesn't look right. It's H2O. So we got the hydrogen ion and the hydroxide ion, and when you put those together, that makes a water molecule. So the net ionic equation for an acid-base reaction that has a strong acid in it is always going to be the same. It's not what I wanted to do at all. It's going to be hydrogen ion plus hydroxide ion makes water. What about those other ions? Well, the sodium and the chloride, they came to the beaker with their friends hydrogen ion and hydroxide ion, and they're still there in the beaker, but nothing happened to them. So in the net ionic equation, since they weren't actually involved in the chemical reaction, we don't include them. Because this same reaction would have occurred even if those ions had been different. If it had been potassium instead of sodium, the net ionic equation would be exactly the same. So here's looking at the same reaction here between hydrochloric acid and sodium hydroxide. So hydrochloric acid is a strong acid, meaning it ionizes completely. And so all of these chloride ions have lost a hydrogen ion, but that hydrogen ion is too small to be out by itself. So those hydrogen ions are riding around on a water molecule. Okay? kind of like a babysitter. Over here, we've got sodium ions and hydroxide ions. And when these mix together, this hydronium ion is like, get this hydrogen ion off my back, like literally. And then here's a hydroxide ion, and this has a negative charge, and that has a positive charge. And so they get together and they make a water molecule. So here we're not really seeing the water molecules that got formed because they just mix in with the gazillions and gazillions of other water molecules that were already there. And so what we've got left here is literally salt water. So you mix the right combination of sodium hydroxide and hydrochloric acid and you end up with salt water. Okay, these are some common common acids and bases. In one of these years, I'm going to move this up. So these are the strong acids. There's 6 of them. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, and perchloric. Any other acid is a weak acid. There's lots of other weak acids. We don't run into very many in Chem 1A, but these are some examples. We recognize that these are acids because they start with H. But if we're writing a net ionic equation, we're not going to separate these into the individual ions because they don't do that very much. They only do it a tiny bit. These are weak acids. They are weak electrolytes. They're mostly intact molecules. And then we have the bases. So these would be considered strong bases in that they ionize completely. Well, really, they dissociate completely. They are soluble ionic compounds. They're metal hydroxides. And the only weak base you need to be aware of is ammonia. So ammonia is NH3, which doesn't look like a base, does it? Doesn't have OH in it. What happens, though, is that NH3 will react with water, and this NH3 will take the hydrogen ion from water to become ammonium ion and hydroxide ion. And so this meets the definition of a base because it forms hydroxide ion in water, even though it doesn't contain any hydroxide. Write a molecular and net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So we're going to be thinking about swapping ion partners. So we're going to write down the chemical formulas for the reactants. So we've got HBr and we have LiOH. Those are both aqueous. They told us so. And then what we want to do is below those, write the ions that come from those compounds. So hydrobromic acid produces hydrogen ions and bromide ions. Lithium hydroxide separates into lithium ions and hydroxide ions. And then let's swap the partners and write them next to each other. So H plus and OH minus, lithium plus and Br minus. What do we get when hydrogen ion and hydroxide ion combine? Water. And water at room temperature is a liquid. And what compound would lithium and bromide ions make? Would be the formula. Just LiBr, right? Because this is a positive 1 charge and a negative 1 charge. Is that a soluble ionic compound? Yeah, all lithium compounds are soluble. So that's my molecular equation. You can say, well, that's me, molecular equation. It's not telling us that we have to write the complete ionic equation. So you don't necessarily have to write that out. You have to, though, be able to see it in your mind, if nothing else. And if you're doing this underneath to help you predict the products, basically what we have here is the net ionic equation. This is aqueous, a strong acid. This is aqueous, soluble ionic compound. This is a liquid. So the net ionic equation would not have that as ions. It would show that as H2O liquid. This is aqueous. That would also be individual ions. So then we can look at this and say, well, what things are not changing? Well, did anything happen to bromide? No, it's still aqueous. So bromide didn't get involved. What about lithium? Lithium didn't get involved either. So the net ionic equation is H plus aqueous plus OH minus aqueous, making H2O liquid. And that is the net ionic equation for many acid-base reactions. Any questions? Write the net ionic equation for the reaction between aqueous HCHO2, a weak acid, and aqueous NaOH. Well, we're going to do the same thing. We are going to write the reactants. So I've got HCHO2, aqueous, and NaOH, aqueous. To predict the products, I look at the ions that get formed, I swap the partners, and I put them together in their new combinations. So it's very helpful under the formula for the reactants to write the ions that form. Now, you've probably never seen this acid before. It's okay, you don't need to know what it is. The H in the front is that ionizable proton, right? So the H in the front is one ion, and everything else in that is the other ion. So I've got H plus, and the rest of it is CHO2. And what's the charge on that going to be? -1, right? Because this is a neutral compound, I know that this is H plus. There's only one of those guys, so it's got to be -1. Over here I've got sodium ion and hydroxide ion, and I'm going to swap partners. So there's my H plus and my OH minus, and then I've got sodium ion and the little weirdo there. It's formate. And I'm going to put these two together, so that makes water. Acid-base reactions in Chem 1A, you're always going to get water. And then here, even though I don't know, I'm not familiar with this ion, I can still write the formula because I've got a -1 charge and a +1 charge. I'm going to write them next to each other, NaCHO2. And we can predict whether that's a solid or it's aqueous. We look at the list of rules, and sodium compounds are always soluble, no exceptions. So we don't even need to know what the other guy is. That one's aqueous. I kind of skipped over balancing the previous one because it actually was already balanced. I shouldn't have done that, but let's check this one. So here I have an H, but then I have H here, and I have H there. There's H's all over the place, right? So I do have hydroxide here. That's a polyatomic ion, but I don't really see hydroxide ion over there, right? So we need to balance the hydrogens and the oxygens separately. So this is one hydrogen and another hydrogen. So that's two hydrogens and another one over here, total of three hydrogens. Well, there's two here and one there, so that's three. I have one carbon and one carbon. Here I have two oxygens plus another is three, and one oxygen plus two is also three. And then I have one sodium and one sodium, so this is balanced as it is. So that's the molecular equation. It's asking us for the net ionic equation. So anything that's aqueous might be turned into individual ions. The exception is an acid that is not a strong acid. This is a weak acid, so we're not going to separate it into ions. We're going to write it down as it is. So what I'm going to do is I'm going to write the complete ionic equation. So that's going to be HCHO2. Should I write sodium hydroxide as separate ions? Yeah. This is not a weak acid. So Na plus, aqueous, hydroxide, aqueous. Should I separate water into ions? No, it's a liquid. Solids, liquids, and gases you do not separate. And this guy, should I separate that? Yeah. So aqueous things you separate, except there's one exception, weak acids. So this is not a weak acid. It's not an acid at all. So we'll write that as individual ions. So sodium ions and the other thing. That's the complete ionic equation.
And the one up there is the molecular one?
This is the molecular equation, yeah. This guy. So that's molecular equation. This is complete ionic equation. And then we're going to write the net ionic equation down here. So we want to look at our complete ionic equation and see what's not changing. What is the same on both sides of the arrow? Sodium. Is there anything else? No, there isn't this time. So HCHO2 aqueous plus hydroxide is going to give us water and CHO2 minus. And that's the net ionic equation. Any questions? Acid-base titration. This is a very important topic. You'll be okay if you can't write net ionic equations. You're not going to get a perfect score on the exam, but you'll be just fine. You should still try, right? Especially because if you go on to Chem 1B, we are going to use net ionic equations a lot more, and we have to just be comfortable with them. Students find them disturbing for some reason. But the acid-base titration, we're going to do several acid-base titration experiments in lab this semester, and this is just like one of the core techniques of chemistry. So a titration is a technique where we take a substance that we know the concentration of and we react it with another substance that we don't know the concentration of. And we're going to measure the volumes of both. Usually we use a burette. And then from that, we can find out what the concentration of the unknown thing is. We're going to add one solution to the other until the reactants are in their stoichiometric ratio. That's called the equivalence point, where we've added an equivalent amount of each of the reactants. And then we can calculate the unknown concentration using stoichiometry. So a lot of times this is an acid-base. There are other types of titrations, but we're talking about acid-base. Here, in general, both the reactant and product solutions are colorless. They look like water. So how do you know when you've added enough acid to neutralize the base? You can't just look at it and say, oh, there it is. We add something called an indicator. So an indicator is an organic acid that is intensely colored in one of its forms. Or it's intensely colored in both forms, but the colors are different. So we add that indicator, and the indicator is going to change color when our solution changes from acidic to basic or basic to acidic. And so we see that color change, and we know that we hit the equivalence point. In an acid-base reaction, the equivalence point is where we have the number of moles of H plus is equal to the number of moles of OH minus. So here's an illustration and pictures. Typically, we'll put the sodium hydroxide, or the base, in a burette. And this is why we've been practicing with the burettes, because we're going to need to use these and be competent with them. We'll record the initial volume, the initial reading, and then we're going to add the base from the burette into the acid solution. There's an indicator in here. As the hydroxide is added, it's going to react with the hydrogen ions, right? So it's going to form water molecules. And at the point where all of the hydrogen ions get used up, then it's going to change color. And this is pictures of an actual burette and a titration. And at first, it looks like you're adding water to water and super boring. Then what you start to see is you'll see a little bit of pink in the middle, but when you swirl it around, when you mix it, the pink goes away. So in this picture, some sodium hydroxide has been added, and it hasn't fully reacted yet. It hasn't mixed around enough to fully react. But as soon as we let it mix, then it'll go colorless again. When we get to the end point, 1 drop or even less than 1 drop will cause the whole thing to go pink. Now, this is pink for illustration purposes. What we really want is a very, very pale pink. We don't want, that's like one of my favorite colors, phenolphthalein pink, but that's not the color we want to see in our flasks. So acid-base titration calculations really are just solution stoichiometry problems, which we learned how to do on Tuesday. In this example, the balanced chemical equation is not given. We do need that balanced chemical equation, but today we learned how to write that. So, a titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? Well, we're given a volume of H2SO4, and we have a volume and a concentration of the KOH, and they're asking us for the concentration of the H2SO4. This is stoichiometry. There's a chemical reaction going on here. This is not a dilution problem. We need a chemical equation, because without the chemical equation, we don't know what the mole ratio is, and we should never assume what the mole ratio is. So here is one of my reactants, H2SO4, and the other reactant is KOH. And then I need to predict what products are going to form. So it's a good idea to write the ions with their charges down below, just to make it a little easier on yourself. What we're doing is we're swapping partners and seeing what happens. So we're going to have H+, we're going to have hydroxide ion, and we're going to have K+, and we're going to have sulfate ion. H+ and OH- are always going to be H2O liquid. And then these guys, this is a 2- charge, so I need 2 potassiums. If it helps to draw it out. I need 2 of these so that the total positive charge is equal to the total negative charge. So now I've got all my reactants and products, and then I need to balance the equation. So again, the hydrogens are kind of, and the oxygens are sort of going all over the place. So over here I have 2 hydrogens and 1 hydrogen, that's 3. And over here I have 2. And I'm thinking, well, that sounds like no fun to deal with. Let's try starting somewhere else. Let's maybe start at the second reactant. Let's start with the potassium instead. Well, here I've got 1 potassium, and over here I've got 2 potassiums. Okay, that's easier, right? We need a 2 here. Got that one. Now, we may recognize, oh, sulfate was here, and sulfate is over there. That stayed together. We could balance that as a unit. So that one's okay. But now, let's go back and deal with those hydrogens. So I have 2 hydrogens here, and now I have 2 hydrogens here. 2 plus 2 is 4. Over here I only have 2. Well, that's a little easier to fix than when we had 3 and 2. If I put a 2 there, then I've got 4 hydrogens. And now let's check the oxygens. I was doing sulfate as a unit, so I'm just going to highlight those as inventory has already been done on the sulfate things, so let's not count those. Let's look at the oxygens, the other oxygens. So there's 2 oxygens in here and 2 oxygens in there, and so there's my balanced chemical equation. This is a diprotic acid. It has 2 hydrogen ions, so that's going to need 2 hydroxide ions. So all of this stuff at the bottom was helpful in writing the balanced chemical equation, but it's getting in the way, so I'm going to erase that. On an exam, I'd give you the molecular equation.
That would be nice.
Yeah, but here, we're practicing because we need to know how to do it. I just won't make you write the equation and do the calculation. So now I've got the chemical equation. I can use that to organize my information. So I have 20 milliliters of the H2SO4. Let's make this a different color maybe. So I've got 20 milliliters of that. And it says I have 22.87 milliliters of the KOH. And I have this concentration. What does the capital M stand for? Molarity, moles per liter. So I want to write moles per liter so that my brain recognizes there's a fraction involved there. That's a conversion factor. And then it says, what's the concentration? That's the question. Question mark, moles per liter. So this is stoichiometry. All titrations are stoichiometry. And where do we start? Grams to moles to grams. We're not always going to stay there. but that's a good place to start. Grams to moles to moles to grams. Well, do we have any masses? No, we don't. We've got solutions. So in solutions, we're looking at volumes instead of at masses, right? Now, in this problem, are we trying to find the volume of a solution at the end? We're trying to find the molarity. So actually, we don't want to go here at all. We want to calculate the moles of that, and then we have the volume, and to find the molarity, we take the moles and we divide by the volume in liters, right? So we're going to do stoichiometry, liters to moles, and then we're going to use the equation that molarity is equal to moles divided by liters. Well, this is in milliliters. So we could add an extra step at the beginning, or we could do that little cheat thing that we've been doing.
Yeah, let's cheat.
Yeah, 22.87. Then instead of writing the small m, milli, we write what it means, times 10 to the minus 3. So 22.87 times 10 to the minus 3 liters. So we kind of just knock that one off. So I'm going to start with volume, 22.87 times 10 to the minus 3 liters, and that is of the KOH solution. And I'm going to convert that to moles of KOH. And then I'm going to go to moles of H2SO4. And I'm going to stop there. So I'm going to bring liters down here to cancel out. I'm going to bring moles of KOH down here to cancel out. Dimensional analysis once again. The moles per liter for KOH is right here. 0.158 moles. 0.158 moles per each liter of KOH. Where does the mole ratio come from? The balanced chemical equation. 1 mole of H2SO4 reacts with 2 moles of KOH. 1 mole of H2SO4 reacts with 2 moles of KOH. What I like about this approach is that there's an awful lot less thinking. Because I don't know about you, but when I think, especially under pressure, I get things twisted up sometimes. And then I'll start arguing with myself, and nothing makes any sense anymore. Right? But if I follow this pattern and I put the units in there, I can't argue with that. Well, I had liters, I need to divide by liters here. And the units go in there, and then the units are telling me where to put the numbers, so I just put them there, and then I do the math. So 22.87 EE negative 3 times 0.158 divided by 2. 0.00. We should have 3 sig figs because this has 3 sig figs. 0.01867 moles of H2SO4. That's not our answer yet. The molarity of that solution is equal to the number of moles divided by the volume in liters. Well, they gave it to me in milliliters. Well, we'll show them. 20.0 times 10 to the minus 3 liters. There we go. Be careful when you divide by a number like this that you're using scientific notation on your calculator correctly. Otherwise, you'll end up with something that's like 1,000,000 times too big. That's not good. you end up with 1,000,000 times too small. And it would be very wrong. It'd be very wrong. So, moles per liter. And so I'm going to round that to 3 significant figures. And I can write the units as moles per liter, or I can say 0.903 capital M. And that's the concentration. Molarities of solutions are generally going to be relatively small numbers. Something like 16 is huge. There are things that are 16 moles per liter, but not very many. Most of the concentrations we're going to see are probably going to be like 2 or smaller. A lot of them will be less than 1. So like 0.09, that's a typical concentration. Any questions?